Chapter 27. The space-time continuum of the general theory of relativity is not a Euclidean continuum. In the first part of this book, we were able to make use of space-time coordinates, which allowed of a simple and direct physical interpretation, and which, according to section 26, can be regarded as four-dimensional Cartesian coordinates. This was possible on the basis of the law of the constancy of the velocity of light. But, according to section 22, the general theory of relativity cannot retain this law. On the contrary, we arrived at the result that according to this latter theory, the velocity of light must always depend on the coordinates when a gravitational field is present. In connection with a specific illustration in section 23, we found that the presence of a gravitational field invalidates the definition of the coordinates and the time, which led us to our objective in the special theory of relativity. In view of the results of these considerations, we are led to the conviction that, according to the general principle of relativity, the space-time continuum cannot be regarded as a Euclidean one, but that here we have the general case corresponding to the marble slab with local variations of temperature, and with which we made acquaintance as an example of a two-dimensional continuum. Just as it was there impossible to construct a Cartesian coordinate system from equal rods, so here it is impossible to build up a system, reference body, from rigid bodies and clocks, which shall be of such a nature that measuring rods and clocks, arranged rigidly with respect to one another, shall indicate position and time directly. Such was the essence of the difficulty with which we were confronted in section 23. But the considerations of section 25 and 26 show us the way to surmount this difficulty. We refer the four-dimensional space-time continuum in an arbitrary manner to Gauss coordinates. We assign to every point of the continuum events four numbers, x1, x2, x3, x4 coordinates, which have not the least direct physical significance, but only serve the purpose of numbering the points of the continuum in a definite but arbitrary manner. This arrangement does not even need to be of such a kind that we must regard x1, x2, x3 as space coordinates and x4 as a time coordinate. The reader may think that such a description of the world would be quite inadequate. What does it mean to assign to an event the particular coordinates x1, x2, x3, x4, if in themselves these coordinates have no significance? More careful consideration shows, however, that this anxiety is unfounded. Let us consider, for instance, a material point with any kind of motion. If this point had only a momentary existence, without duration, then it would be described in space-time by a single system of values, x1, x2, x3, x4. Thus, its permanent existence must be characterized by an infinitely large number of such systems of values, the coordinate values of which are so close together as to give continuity. Corresponding to the material point, we thus have a unidimensional line in the four-dimensional continuum. In the same way, any such lines in our continuum correspond to many points in motion. The only statement having regard to these points which can claim a physical existence are in reality the statements about their encounters. In our mathematical treatment, such an encounter is expressed in the fact that the two lines which represent the motions of the points in question have a particular system of coordinates x1, x2, x3, x4 in common. After mature consideration, the reader will doubtless admit that in reality such encounters constitute the only actual evidence of a time-space nature with which we meet in physical statements. When we were describing the motion of a material point relative to a body of reference, we stated nothing more than the encounters of this point with particular points of the reference body. We can also determine the corresponding values of the time by the observation of encounters of the body with clocks, in conjunction with the observation of the encounter of the hands of clocks with particular points on the dials. It is just the same in the case of space measurements by means of measuring rods, as a little consideration will show. The following statements hold generally. Every physical description resolves itself into a number of statements, each of which refers to the space-time coincidence of two events, A and B. In terms of Gaussian coordinates, every such statement is expressed by the agreement of their four coordinates x1, x2, x3, and x4. Thus, in reality, the description of the time-space continuum by means of Gauss coordinates completely replaces the description with the aid of a body of reference, without suffering from the defects of the latter mode of description. It is not tied down to the Euclidean character of the continuum which has to be represented.